So now let's take a look at how we can kind of summarize the types of substitutions that we're going to be attempting to do in this section. We've already kind of seen that there's a lot of different pieces that kind of go into creating one of these substitutions. Let's start by just recapping what we already saw up above. We started with an expression that had like an a squared minus an x squared, and we did a lot of different things with it. First off, we started by saying that we would use x equals a times the sine of theta to perform our substitution. That was one piece that we had. Of course, from that we were also able to generate a dx. But we also saw near the end of the last video that I needed to go ahead and find a restricted range on my value of theta, so that way I could get rid of absolute value bars that popped up as a result of this substitution. So here we had our value of theta existing from pi over 2 to negative pi over 2. Remember, that's where my cosine would always be positive, and so I could use that range of angles. It wasn't the only range, but we'll see in some later videos why this range is particularly convenient. We'll also notice that there was an identity that we used to go ahead and simplify some things down. Specifically here, we used a 1 minus a sine squared of theta to be equal to a cosine of theta, or cosine squared of theta, excuse me. And this isn't the only substitution I could do here. I could also do something like an a times a cosine of theta. If you kind of recap what we did in the last video, remember that we chose the value of a because it would help us to match this a squared that was already a part of the radical. Then we could factor that out. 1 minus the sine squared was very convenient because that allowed us to use an identity to get a cosine squared. We could do the same thing by selecting a times cosine. However, I'll just record it here like this. Now, if I think about some other expressions that I could work with, suppose that I had an expression that looked like a squared plus x squared. If I wanted to do a substitution here, you could probably still imagine that I'm going to start with the value of a. So I can imagine having an a squared and an a squared that could be factored out. However, once factored out, keep in mind I would have something like a times 1 plus something else being squared, which would be the trig function that I have. And so I'd like to start to try to think, what trig function, being squared, could I add 1 to that could generate some sort of an identity for me to simply work with? Well, there's a couple different options. You could actually select a tangent of theta or a cotangent of theta. Now, take a look here as I'm kind of scribbling down loosely what some of the scratch work would look like. Notice that if I had a 1 plus a tangent squared being pulled in here, I could use the identity that 1 plus a tangent of theta is equal to a secant squared of theta, which would leave me with a secant squared of theta under my radical. When simplified down, this would produce a and an absolute value of secant. That should be secant to the first power there. So just pretend that's scribbled out. So if this is a times secant to the first of theta, and I want to make that always positive, I again could think, what would be values of theta that I could use? Well, actually here, I can see that if I go back to my unit circle, I can actually select pretty much the exact same values, probably just excluding the endpoints, since that's where the secant would become undefined. But I've been able to simplify down the radical using my substitution here, and then with the appropriate angle restrictions, I could get rid of those absolute value bars. Now, this is a complicated process to work with, and we have one more expression that we want to try to deal with. What would happen if I had something like an x squared minus an a squared? Well, here I would actually go ahead and choose something kind of like the following. I'd have an a secant theta, and my angle restriction is going to be very, very strange. I would actually have theta somewhere from 0 to pi over 2, or from pi to 3 pi over 2. We'll come back to that here in a moment. I would also be able to use an identity of secant squared of theta minus 1 is equal to tangent squared theta. Now this last row is kind of confusing and a little bit weird to see, but to help try to understand why, I'm going to ask you to try to take a look here at example number 1. Can you try to go ahead and see how you would actually begin to simplify this radical down if you were using this substitution and this angle restriction? Pause the video really quick and see if you can work through this. And of course, when you hit unpause, you'll see me working through the solution. Alright, so if I was working on this and I made my substitution, notice that that would produce for me a squared secant squared theta minus a squared. That a squared is now a common factor that I can pull out. Oops, and I wrote this down in the wrong order. That should be secant squared of theta minus 1. Of course, secant squared minus 1, we see up above, is the same thing as a tangent squared. When I simplify this down, I know that that's going to create a times absolute value of the tangent. And so I'd have to figure out, how do I determine if my tangent, or how do I determine if my tangent function is always positive? I mean, we know it's not, so where would it be positive? If I think quickly about my unit circle, I can recognize that my tangent function is going to be positive when both the sine and cosine are positive, or the sine and cosine are both negative. Notice that would be the range of angles 0 to pi over 2, and pi to 3 pi over 2. So with the given angle restriction, I can actually go ahead and simplify this down to a times the tangent of theta. This is why I need this kind of strange angle restriction over here, so I can cover all possible values of the tangent.